Next in the session, we'll see structures and unions concept. So after functions, structures and unions are the when next set of advanced concepts. Okay? And after this comes the pointers. And again, using pointers, we can extensively use pointers in functions. So then again, we'll revisit the functions when we learn pointers. Okay. So in this course, so I am keeping structures and unions now. So let's see slightly basic and little advanced structures. So first of all, just to see the definition, what are structures? So structures are nothing but these are the user-defined data types. Okay, sorry for typo. These are user-defined data types which allow us to group different elements of data under one name. Okay, but whereas we saw array, in array we can have just one integer and 10 of those types. Okay, or 10 floats of those type, 100 floats of the same type. But whereas in structure, if you see here, I can have a structure and I want to have one integer and another integer. I can also have one more character in this. Okay. But the point what I'm trying to make here is in the array, what you saw, you are collecting similar type of data. But whereas here you are structuring the data in a more sensible way. Okay. And this gives programmer a very good idea about the structure of a data. Okay, say you have a bank software where you have name, bank balance, interest, debit, everything. So you need not create 100 names. Okay, what you create is one structure. Name is one element, okay. One member. His principal or the remaining balance is one element. Rate is one element. And then if there is any debit, that is one element. Then you use the same structure for all the bank members, all the bank account holders, then you will be able to, it looks more structured. So that's why the name structure, I guess. Okay. So this we'll see in the C code examples. Next in the structures, what we have is what we saw here is SAL, SAL and rate. These are called the structure members. So these two are the members of payroll structure. What is user-defined data type in this? This is user-defined data type. Okay. Payroll is user-defined data type. And the member of this payroll struct are int and rate. Okay. So that's what I'm trying to tell here. And this is accessed. Each member is accessed using a dot operator. This we will see. Okay, I have explained it here, but we'll see this in detail in the code example. Yeah. So say this is a struct payroll, and this is how we access the member. Yeah, p dot. And now next, what will be the size of a structure? So this is little important as well as a tricky part. Okay? So just going back to the original example, if you see here, the size of integer is 4. So we have two integers here. So the size of this structure will be 8. So this is clear. But whereas if we have one more element like character, then the size of structure is character is 1 byte, integer is 4. This is 4. So ideally the structure, the length or the size of a character, size of a structure should have been 9, but it will round off to the next 4 byte boundary. Okay. That is mostly for the memory alignment. Okay. So what does it do? Then comes the structure padding topic. It's connected to that 4 byte alignment. Okay. The structure always tries to align itself to a 4 byte file, 4 byte memory alignment. Okay. So when it tries to do 4 byte memory alignment, so say you have a character, integer and integer. Then when you align it 4 bytes, then you have to do something with the 3 bytes which are not used, what we're to do with those 3 bytes which are extra, okay? Because we cannot access them, but they still occupy some memory for the memory alignment purpose. So those will be filled ideally with 0, or we can do an explicit padding of those bytes. Okay, explicit padding is always recommended. Okay, if the alignment is not omitted using a hash pragma. So that's because you can port it to any controller or any compiler. Yeah, meaning today you are using it in this project. Your reusability of that code increases when you do a explicit padding. Okay, we'll see what is explicit padding means. I'll just take you to the code blocks to demonstrate something. Yeah. So we have it here, and then now I will write a standard function into main. And then before this, let's define one structure, our own structure. I will have one more character C to cover the wider range of topics. So here, in the definition, what we saw is we called the structure a user-defined data. Okay, here, what I am doing here is I created my own data type payroll of type which has a characteristics of this. Okay, the characteristics of take a standard data type. This is standard data type integer. So what does it do? It will have one integer array. What it will do? It will have a same type of variable of arranged one after the other, and which can be accessed using different names or using the square brackets. But whereas this one, this is my own data type. Okay, according to my need, I created. I can access a character. I can store a integer, and I can store an integer. Okay, so just the way we define the integers. Okay, this is how we define integers, right? Int x, integer is a data type, x is a variable. Similar thing we'll do, only extra is we add struct payroll p. So this thing is a user defined data type, and this is a variable of type p. Correct. So now what I'll do, I'll just initialize this and print. Okay, so what we saw is we access the elements using dot. So that value of san is, yeah, we are writing ampersand d. That's because p dot san, what we are writing, this is at the end the integer in itself. Okay, only thing, this integer is accessed via this p root, p structure. Let me compile it and see this is printed correctly. Yep. So next what we'll see also the size of, yeah, and in the same example, size of p is how do we calculate size of? We use this operator size of. It's a standard library. We can write p or payroll, both are possible, like how we used to write int or a variable name itself. What we have 12. The size of p is 12. But whereas if you see this character is 1 byte, integer is 4 bytes in size, and this is 4 bytes in size, but the size of function is returning 12. That's because it has considered the padding also. Okay, that's what we were explaining before we were discussing that, right? So we can also do a explicit padding here. Char c pad. Okay, I'm using my own variable 3. Now we'll see the size of p still remains same. Size of p, that is the structure, is still 12. Okay, So next, the moment I add one more char, it will go to 16 now, because it will get aligned to 4-byte boundary. The size of P is 16. So this 1 byte, these 3 bytes, 1 byte, 3 bytes of padding, 4 bytes, 4 bytes. Okay. So a better way, when you have two different characters, in this case, okay, I removed those 3 bytes extra. So now we can see this is still 1 byte. Okay. Now total 10 bytes. So first one character, one more byte, 2 bytes of padding now, and then 4 bytes, 4 bytes. So we can see the size is still 12. Okay. So how long it will be 12? I can do E, one more byte it can accommodate. S, yes, till here it will be 12. So when you're defining a structure, it's always better to take the smaller data types at the beginning. Okay. So let me show you an example here. I mean, the same structure. Okay. So what we saw is size was 12. Now what I'll do, the moment I take this out and paste it here, do you think the size is still 12? Let's do the static analysis first. See 1 byte. Next, there is no 1 byte variable. It's a 4 byte variable. Okay. So it will fill 3 bytes, 4, 1, 3 byte fill 1. So here the size is actually 16. Let's see if this is correct. Size is actually 16. Okay. Just by rearranging, you can reduce the size. And this is how, this is a recommended way to define the structure members. Okay. First, define the smallest data types so that they occupy a memory, and they will round off themselves to a nearest 4 byte boundary, and next the bigger ones. Okay. So using this, what you're doing is you're grouping these two first in a memory arrangement, and then 2 bytes of padding, and then 4 bytes allocation. Okay. Now say you don't want this, you don't want alignment, you just want plain 10 bytes. Okay. So this is the syntax I'm using, pragma pack. Yeah. So if I do this, the size of gets reduced to 10. You can see the size is reduced to 10. But it has its own drawbacks. Yeah, because usually the controller or the memory architecture of a system should be valued. Okay, meaning if something is 4 bytes, and if you want to access this element at a faster rate, you want it to be present at 4 byte boundary. Okay, the structure has to, I mean, this is the usual recommendation, not to use pragma unless you have a real memory crunch. So this is one way of reducing the memory padding. And what does pragma make is sometimes another compiler might not support the padding, or that always supports the padding. So in that case, porting the same code to a different compiler will become an issue. So usually in the industry, you will get different warnings for such use cases. That it will tell you that it will throw a warning telling compiler dependent code. Okay, so we should make the code as independent as possible.